Hello and welcome to Talking SoS, a video series on the science of security with Shawn Riley. In today's episode, we're going to talk about cybersecurity science and symbolic AI, or artificial intelligence. These are probably two of my favorite subjects in the whole world. So today we're going to cover what is science, what is cybersecurity science, operational cyber defense knowledge, three sources of knowledge, symbolic AI and non-symbolic AI. Symbolic in this instance just means human readable. So human readable AI and non-human readable AI. Four types of knowledge models: cognitive playbooks, experience, claim evidence reasoning, argumentation, and comparing symbolic AI or human readable AI and non-symbolic AI. So science is really about making sense of the evidence, and we do that by investigating the evidence so we can make sense of it and explain it, and then those explanations are critiqued over time. As more evidence becomes available, we can critique those explanations and update those explanations based on new evidence. So when we think about what is cybersecurity science, this first paragraph comes from the NSA Science of Security Virtual Organization, and it's really kind of a part of their description of what cybersecurity science is, but it's the part that I thought was the most meaningful for this series on cybersecurity science in the operational environment. So cybersecurity science is really taken to mean a body of knowledge containing laws and axioms and provable theories that provide objective and qualitative or quantifiable descriptions of security properties and behaviors that transcend specific systems, attacks, and defense mechanisms. And this second paragraph really comes from the Joint Statement of Understanding from the nations of the United Kingdom, Canada, and the United States, where they agree that there are 7 core themes that are strongly interrelated and mutually inform and benefit each other in the science of security discipline. And those are common language, core principles, attack analysis, measurable security, risk, agility, and human factors. So obviously there can be, and you often hear most about cybersecurity science in the research context because it's coming from the publication of different papers and different journals and stuff where it gets picked up by media and people writing articles on the internet, and it generally gets a lot more coverage in the science sense than operational cybersecurity science. If you think about, our operational cyber defense ecosystem, there is a ton of observations from a growing number of sensors in that environment that we investigate the observations coming from those sensors so we can make sense of those, so we can explain those observations so we can decide what to do about it, right? And so I'm a cybersecurity scientist who focuses on operational cybersecurity science and building operational cyber defense knowledge. So if we think about cybersecurity science as kind of building that body of knowledge, I want to build that kind of body of knowledge about the operational cyber defense ecosystem so I can understand myself and the organization that I'm defending, but I also kind of want to understand the threats and the adversaries that are out there that are, attacking me. So when I think about foundational operational cyber defense knowledge, and we have to start with the traditional information security knowledge and the traditional confidentiality, integrity, availability, and that focus on governance, risk, and compliance. But from a data and information perspective, this is where we get things like all of that basic cyber hygiene knowledge. So what are all the assets in our environment? What are the networks in our environments? What are the devices in our environment? What are the operating systems and software applications in our environment? What are the users and privileged users? What are the configurations and services in the environment? And we want to understand, how do those different assets, those network services, devices, people, support different parts of the business or the mission? We also want to understand what threats kind of align to the technology that we're using and the type of business that we're in, what industry we're in. So that way we can then look at the security controls and resiliency techniques and intelligence and courses of action that we need in order to protect, detect, respond, and recover from the threats that we're facing, and kind of organize that cyber defense knowledge together so we can use it in an efficient and effective way. So where does knowledge come from? Well, we kind of get knowledge from three primary sources. When we think about looking at the data in our environment, we can use inductive inference. Inductive inference establishes new facts from data. It's called the bottom-up method. So it's really looking for the patterns in that data and saying, hey, this is probably this, a threat or a risk. And that inductive inference will produce information about the data. So it's producing the new facts from the data. We can also get information shared by others, such as threat information sharing or vulnerability knowledge from the National Vulnerability Database. And we can get that information communicated from others where they've developed that knowledge through other means. We can also use deductive inference. Deductive inference is where we take our individual knowledge or our organizational knowledge or our industry knowledge and use that along with deductive inference. Deductive inference establishes new facts from existing facts. So if you think about, you get information that, hey, there's an unauthorized PowerShell event, you might infer, well, that's the adversary attempting the objective of execution. And that's a fact that you deduced out of, say, MITRE's attack knowledge into that situation based on the fact of it being a T1086 technique for unauthorized PowerShell. So when we think about looking at those three types of knowledge in the context of artificial intelligence, both symbolic artificial intelligence and non-symbolic artificial intelligence align perfectly without really competing with each other to this way of thinking about artificial intelligence. So if you think about non-symbolic artificial intelligence or the machine learning data science side, where they're applying data science and machine learning algorithms to the data, they're using inductive inference to make predictions, right? So predictive analytics, machine learning, they're applying inductive inference to make those predictions about the patterns in the data. Symbolic artificial intelligence is the side that focuses in on knowledge, because remember I said that symbolic in this case means human readable AI. And that's because symbolic AI really focuses in on, how do I capture human knowledge and experience, so that way it can then mimic the way that we reason or deduce information based on the knowledge. So it operates using deductive inference in the same way that Sherlock Holmes would deduce facts based on the evidence that he's looking at, right? So this top side, symbolic AI, uses knowledge engineering, whereas non-symbolic AI uses data science. When we think about symbolic AI and that knowledge engineering, it's important to understand the four primary types of knowledge models that are commonly used within IT. So in this graphic, on the up and down axis here, it's really representing weak semantics to strong semantics, where as you move up, it's increasing it's being more explicit in the types of knowledge models that you use. So it's increasing in metadata, context, and knowledge representation. As we move over to the right along the bottom, you can see increasing reasoning capabilities. So recovery, discovery, intelligence, question answering, smart behaviors. And then here in the center along the line, we see different types of knowledge models, and we can kind of summarize these into four basic types that we see in the IT environment. Down here at the very bottom, where you see kind of controlled vocabulary, that's kind of another way of saying dictionary. And dictionary is the most one of the most common types of models that we see. Just above a dictionary is a taxonomy. And so if you think about examples of taxonomies, MITRE's enterprise attack is a taxonomy of adversary tactics and techniques. STIX is a taxonomy used for structured threat information expression. And it comes with the JSON schema, right? That would align there. Just above a taxonomy is a thesaurus. So it's a little bit more explicit than a taxonomy, but not as explicit as an ontology, which is a type of conceptual model. So ontologies are generally up here within IT environments and within science. Ontologies generally mean OWL, the ontological web language from the W3C, as a standardized language for writing ontologies. And ontologies often use description logic. And the other important thing to point out is taxonomies and XML schemas and JSON schemas, they really focus in on syntactic interoperability and at the most structural interoperability, because they're generally focused in on their specific silo. Whereas ontologies are more focused on integrating knowledge, so integrating different silos of information into integrated knowledge, and for that you really want semantic interoperability. So this way you understand that a STIX attack pattern, for example, is the same as a ODNI cyber threat framework layer 3 action, which is the same as a MITRE attack technique. All of those are kind of equivalent objects. And so when you think about integrating knowledge from those three different sources of STIX-based threat intelligence, MITRE's enterprise attack knowledge, and the ODNI cyber threat framework for consistent characterization and classification of cyber threat events, you want to make sure that you can think across those and have semantic interoperability across your knowledge. And that's where you really focus in on ontologies. So ontologies are really used to represent, the information and the context. But when we get into the human expert experience, that goes with using and applying that knowledge, using that information and context, we need to be able to capture that human expert experience in a way that the AI can understand and operate in, so they can mimic the human expert experience in applying that knowledge. And we use modern expert systems and modern knowledge-based systems use a concept called a cognitive playbook, where you basically capture the step-by-step cognitive process of a human expert to pull in data feeds with evidence that you're then going to investigate and go through a process of validating whether or not this is good or bad, and how you make that decision, capturing that process, so that way you can then make claims about the evidence based on the facts of the evidence. So that way you can then reference the reasoning engine that will allow you to access those ontologies and the knowledge models. So that way you can then, based on the facts that you've identified coming from the evidence, use those knowledge models and the knowledge encoded in those. So your knowledge model of, say, MITRE's ATT&CK, and the knowledge model of the ODNI cyber threat framework, for example, and the knowledge model of STIX for threat intelligence, looking at, say, this Windows evidence coming from Windows events or Sysmon events for PowerShell events, and identifying that, hey, this is a malicious PowerShell, that it's a T1086. So then I want this reasoning engine to infer out of those knowledge models things about this incident, and to infer that this technique of the T1086 is the adversary attempting to achieve the execution of, or the objective of execution. And it's in the ODNI cyber threat framework, stage 3 of the cyber attack lifecycle, where the adversary is attempting to establish a presence in the victim enterprise. So, and then we want to make sure that we relate any of the claims that we're making to the evidence, so that way that's all tied together before it gets published to memory. And this is really just that human expert saying, hey, if I was looking at it, these are the steps in the process that I would go through. These are the knowledge models that I would use to add additional information and context to this investigation before I send it on to the next step. And you're just capturing that cognitive process and the human expert experience and what they're doing. So the AI can then not only follow that cognitive step-by-step process, but apply that reasoning and inference, that deductive inference, into that investigation. So those cognitive playbooks allow us to capture that human expert experience, but that human expert experience can also use that, or that human expert can also use that cognitive playbook to automate the claim evidence reasoning process or framework. This is often used in science to make scientific arguments, or to make a explanation based on the evidence. And so really, when you think, well, what is claims evidence reasoning? A claim is, what do you know? And evidence, right, those structured observations that we're getting as window event logs or coming from Sysmon, they were our evidence, and that was how we knew that, right? And the scientific reasoning was, why does the evidence support the claims that we were making? So how did that evidence support that that was a non-authorized PowerShell, right? And it's because we looked in the kind of step-by-step process that it wasn't an authorized user doing it. So when we think about producing arguments, whether it's a scientific argument because you're doing scientific reasoning, or just creating a regular argument or explanation based on non-scientific reasoning, there are different types of claims that you can make. And we've identified 5 primary types of claims that you can make The first one is a definition, right? So you think about pulling some of the knowledge out of your different knowledge models or ontologies. Pulling in a definition might be kind of important if your expert system, your symbolic AI, is talking to a non-expert, right? So think about through the scenario of that unauthorized PowerShell event in the environment, right? That T1086 technique from MITRE's enterprise attack. Well, the objective or the tactic of that is execution. So you could imagine, a non-expert getting this and going, ooh, you're telling me that this PowerShell activity, that its objective was execution? So it was trying to kill me, right? So that isn't exactly what we mean. So we might want to pull in the definition of what the tactic of execution in the context of this investigation means, right? So that way everybody has a shared understanding of what this claim is making, right? And the facts. Did this happen? Did it exist? The value, right, of claim of value. Is this something good or bad? And how do we go about deciding whether it's good or bad, right? So we went through the process of deciding that this PowerShell activity was bad because it was unauthorized. So claims about policy. What should we do about it? What should be our future course of action, right? So you might detect this unauthorized PowerShell activity and go, oh, I need to take the following courses of action to respond to this. And then a claim of cause and effect. What caused it and what are the effects, right? So if the adversary is attacking me, that's going to cause some effect on my business or mission because I'm going to have to stop what I'm doing and respond and recover from that attack. And I'm also going to have to understand that every action that I have in response to the threat actor and their activity is going to have some effect on them. And I need to understand what that effect will be. But understanding kind of the ability to automate claims evidence reasoning in the cognitive playbooks is kind of a key feature of symbolic AI and its support for automating scientific inquiry and scientific knowledge management. So finally, I'd like to compare and contrast symbolic AI and non-symbolic AI to kind of summarize what we talked about over the last couple slides. So if we think about the non-symbolic AI side or the data science side, right, they use machine learning. Machine learning uses algorithms and models that use and apply inductive inference and probabilistic reasoning to make predictions, which are a type of tentative hypothesis, right? This is often considered a black box process because machine learning can't explain why it's making the claims that it's making. Symbolic AI uses knowledge engineering. Remember, this is all about organizing human knowledge and human knowledge in the form of different languages or frameworks or things like that we use, and capturing the human expert experience in applying that knowledge, and that's captured in cognitive playbooks and ontologies that use and apply deductive inference and contextual reasoning, which is generally used to validate hypotheses and explain the evidence in the environment, right? And this whole side of symbolic AI is transparent and explainable because, again, it's just using, integrating, and applying human understandable knowledge. That's it for this time. Thank you for your time and see you next time on Talking SoS.